My name is Miriam Bautista. I'm currently a postdoc at Lawrence Berkeley National Lab, and I'll be presenting to you our preliminary work towards automated superconducting circuit calibration using deep reinforcement learning. And together in this study are my colleagues from the lab, namely Jackie, Anastasia, Mekina from the Computational Research Division, and Mariam Kiran from the Energy Research Network. So the outline of my presentation are as follows. I'll give a little bit background of some of the implementation of quantum circuits, and then followed by the motivation of our proposed optimization. And I'll give also a short background of superconducting circuits and how we use this to model our transmut and to demonstrate entanglement, and our proposed optimization using reinforcement learning, and then some of our preliminary results. So most proposals of implementing quantum circuits have been based on the macroscopic degrees of freedom. So one of these popular approaches is the electron spin control. And the spin of the electron forms the quantum bit, which is the qubit. And the challenge of this system is how to achieve a very fast spin rotation that required to control the qubit without suffering from decoherence. And another popular approach is the use of trap ions. So the qubit based on trap ions can be used to prepare and manipulate some good accuracy, which is shows promising scalable platform for quantum computing. And both of these approaches are quite susceptible to interaction and decoherence, and that's one of the challenges. And another implementation of quantum system is the use of superconducting circuits. And the paper by Deverett and Martinez entitled "Implementing Qubits with Superconducting Circuits" give a really good overview of this approach, and we use this as our reference as we model our circuit. So as motivation, we all know that building a quantum circuit and implementing quantum system is quite difficult, but the promise of this technology, but this is very promising technology, so it's too early to quit, so we still need to continue working hard on this. And one of the challenges is how we would be able to create or to have a good quality qubit. And we need to build a qubit that will be able to generate useful instruction and gate operations on a very large scales. And there are several research efforts on this which are ongoing, and some results are promising, but I think as a community, we're not fully there yet. So current quantum systems still generate errors, as discussed by our previous presenters. So thus we need to implement error correction algorithm that corrects these random errors as they occur. And in order to implement complex algorithm, we need to, including error correction scheme, we need to prove that we are able to control multiple qubits. So that is why quantum optimization is an active field of research today. And in our study, particularly, we focus on quantum optimization in a hardware domain using superconducting circuits. And we propose the automated calibration using deep reinforcement learning. So superconducting circuits really gain attention because of their property of zero resistance when it cooled below its critical temperature, and usually in few kelvins, and therefore the energy dissipation of this circuit is really drastically lower as compared to the standard CMOS implementation. And the fundamental building block of superconducting circuit is the Josephson junction. So the Josephson junction is made of the two superconductors sandwiching a thin insulating barrier such that the electrons can tunnel into the barrier, and then the information is stored in terms of magnetic flux quantum. So the equivalent circuit of the JJ is a coupled capacitor and inductor, which resembles likely as an LC tank resonator. So a simplified model of a transmode qubit coupled to a cavity resonator is used to demonstrate our model for quantum circuit. And we consider the nonlinearity of the transmode qubit coupled to microwave resonator. And this strong nonlinearity is very important to achieve entanglement between these quantum devices. So we analyze the circuit through the equivalent to mode lamp element representation of the distributed circuit and derive the equivalent Hamiltonian translation with the nonlinearity of the Joseph and Junction. And the Hamiltonian of the circuit in the first order perturbation theory described the on diagonal and off nonlinear components. And in our circuit model, we assume a fixed flux transmode. And what we wanted to do is we wanted to maximize the nonlinearity by tuning the qubit inductance. And here in the figure at the right, it shows the simulation of two qubit crossing. The observation of the dark state manifests the coherence of the qubit interaction. And for our optimization, we adopted a deep reinforcement learning. So deep reinforcement learning is useful for finding solution to complex decision making, and it's been used by several groups to solve quantum computing problems like quantum control and error corrections. And here shows the simple block diagram of our DRL model. So part of our environment is our quantum device simulator and our circuit. For our observation space, we the state of the environment, the reward is we look into the error between the trials, and for actions is tuning our circuit components. And in our work, we propose to use deep reinforcement learning, particularly deep deterministic policy gradient. So DDGP is a technique combined Q-learning and policy gradient based on Markov decision process that samples from the environment. And it is a model-free policy-based learning algorithm in which agent will learn directly from the unprocessed observation space. For this case, our environment, we define our environment to be our superconducting circuits. And for our observation space, we look into the tuned transmont inductance, the circuit fidelity, and the energy gap. For actions, we're tuning the qubit inductance. And for our fidelity, for our reward, we look into the fidelity of the system. And here it shows the equation of the Hamiltonian of our model, where the first equation shows the linear piece, and the second part of the equation shows the nonlinear piece, which is a Taylor expanded form. And here shows the diagram of our actor-critic model. So we sample the initial state and action, and then we use this in our model to estimate the return to improve the policy gradient. So the critic estimate the value function with this could be the action value or the state value, and the actor updates the policy distribution in the direction suggested by the critic, such as the policy gradient. And in our training, we use 3-layered neural network. Both the actor and the critic are implemented in the same deep neural network with 2 hidden layers. Each have like 400 and 300 neurons. Also, we adopted a Blackbox circuit quantization method. So the superconducting circuit model is part of our environment. We look at the Hamiltonian energy and the eigenstates of the circuits. For our observation space, we look into the flux, the energy gap, the fidelity, and the density matrix. And for our action, we tune in the magnetic flux of our Joseph and Junction, the inductance of our Joseph and Junction. And for our reward, we look into the fidelity between the circuits, the eigenstates, and the decide states of the qubit. To test our method, we have 3 distinct test environments. We started with a very simple circuit with a coupled qubit and a resonator, and then we have 1 action space, and then we slowly increase the complexity of the circuit until our test environment, we have 2 action space, which is a 2 coupled qubit with a coupled by a microwave resonator. And we run 8 multiple trials in our trainings in each test environment, and we log these following parameters, which is the lost actor, the lost critic, and the rewards, and the best rewards. And the lost actor is the sum of the Q values of the states using the critic network and forwarded to the actor network. And on the other hand, the lost critic is the temporal difference error, where the target network is used to compute the Q value of the next state. And the rewards refers here, which is the value of the mean fidelity of the system. And then the best rewards are the highest fidelity from the cumulative mean rewards per episodes. And here shows the plot of the mean rewards and the mean best reward respectively. So this shows the learning of our algorithm. And then the average best reward that we achieved so far is 0.92, which is 94% of our statically tuned circuit. So we have this, we also compare this one with our statically tuned or manually tuned circuit. And the overall project implementation have 3 phases. So phase, at the moment, we only implemented phase 1, so which is part I am presenting at right now, which is the training phase, where our AI learns to map between the output and the input, and then we retrieve this one into the neural network. And then the next phase of that will be testing phase, and then the third phase is testing with online learning. So the goal of this, we introduce to you our initial work, is just to provide a valuable reference for researchers are also working on circuit optimization and automations. So in summary, I introduced to you a circuit QAD model to simulate entanglement of circuit quantum electrodynamics, and we also demonstrate the viability of the deep reinforcement learning using deep deterministic policy gradient for superconducting circuit optimization and automation. And for our future work, we wanted to increase the complexity of our circuit by testing our model with multiple action spaces. We wanted to, the next step is tuning the hyperparameters and experiment with multiple agents, and also explore different techniques to learn optimal policy. And I would like to acknowledge also the members of our group from this research, Makina, Miriam, Anastasia, and Jackie, and also the funding that we got from this work from the Berkeley Laboratory Directed Research and Development Program. Thank you so much. And if you have any question, feel free to ask me.
Oh, thank you, Miriam. I did want to ask one question about the optimization with the learning network. How long does a typical test take for those plots that you were showing?
Here, so this plot, the runtime. When I run this training, I think the runtime is around 24 hours. So I just leave the training into 24 for overnight and get this result. So as you can see, it stops at 100,000 steps. But I think as we continue the training longer, it would give us a better best reward. So it might take a longer time.
Is that just the complexity of the training piece, or is that the device itself and the sampling?
I think we need to work on. We would still need to work on our algorithm to make it more the runtime faster, because the circuit is quite simple. So we only have the basics qubit and resonator. We still need to work on some of our hyperparameters, and that's one of our next step. Maybe tuning the hyperparameters would also improve the runtime.
Okay, wonderful. Well, hey, thank you very much.